Hello and welcome to this new edition of Thermo 2 videos. Today we're going to be talking about psychrometrics, which is the study of moist air. So what is moist air? Well, for the purpose of engineering analysis, this is a fluid that we're going to model as a mixture of two perfect gases as before. One of them being air, or I should say dry air, which is the stuff that we breathe, which has a molecular mass of 29 kilograms per kmol, and which constitutes a mixture of nitrogen, oxygen, and argon to some extent, although we can also truncate it to nitrogen and oxygen, as well as water vapor, which itself is like steam and is present in moist air. That's what makes the air moist, has a molecular mass of 18 kilograms per kmol. Since it's a mixture of perfect gas, we can apply Daltons Law to this mixture, which means that our total pressure is going to be equal to the sum of the two partial pressures, that of dry air and water vapor. So that's our total pressure. The state relationships are going to be defined for this mixture, just like we've previously done as for mixtures of ideal gases. And specifically, we're going to be talking about enthalpy, but we can repeat it fairly straightforward for internal energy as well. So let's see, for enthalpy, we're going to have the enthalpy of the total mixture, which is going to be a function of temperature. That's going to be equal to the enthalpy, the extensive enthalpy of air plus the extensive enthalpy of the vapor, which is equal to the mass times the specific enthalpy of either one of them. And since we're dealing with perfect gases, the enthalpy is the sum of, the product of the specific heats at a given temperature times the mass that we have at that particular point. So the specific heat times the temperature. And so now we need to define a few new variables that we're going to be using. The mass of dry air, m sub a, the mass of the vapor itself, m sub v, and the total mass, simply m, which is going to be the sum of m sub a plus m sub b. We're also going to define m sub f of x for some constituent x, either air or vapor in this case, as the mass fraction of that constituent in the mixture, m sub x over m. All right, so here we have our expression for the enthalpy, or the specific heat of the total mixture times the temperature, which is equal to the mass of each constituent's mass fraction times its own specific heat times the temperature. And for a internal energy analysis, the same goes for CV times T. This is CV times T, not CV of T, by the way. For the entropy, the total entropy at a given temperature and pressure is going to be equal to the entropy of both constituents summed up. So back to Dalton's Law. Recall that Dalton's Law states that the partial pressure of a gas in a mixture is equal to the mole fraction of that gas times the total pressure of the mixture. And if we rearrange that, that tells us that the mole fraction of the constituent, say constituent air, is going to be equal to the pressure of air, partial pressure of air, over that of the total pressure. And similarly for the water in the constituent as well. So plotting this on a TS diagram now to illustrate where we're at when we're dealing with moist air. This is a TS diagram for the water constituent in the mixture specifically. And what I want to illustrate here is where we are normally when the air is not saturated, when we have a certain relative humidity, which we'll talk about in a moment, and versus when the air is fully saturated. So in the case where the air is not fully saturated, we're going to be somewhere in the superheated region of the dome at the given pressure, vapor pressure that we're at, and that vapor pressure typically is going to be quite low, so lower numbers than we've been dealing with before. And the saturated pressure at that same temperature, the temperature of the moist air itself, is going to be the point at which the air has a relative humidity of 100%. So the gap between those two pressures is directly proportional to that relative humidity, which we're going to define next. So there are two ways to look at humidity, actually. Relative humidity is just one of them. But it's an important one, of course. Starting with that one, the relative humidity, which is designated by the single phi, is defined as the mole fraction of water in the moist air sample that we're looking at, divided by the mole fraction of water in a saturated mixture of air-water at the same temperature and total pressure as the sample that we're dealing with. So that would be P total, for example. And so that means that phi is equal to the y sub v, which is a mole fraction of water in the moist air, divided by y sub g, or y sub v sat, at that temperature and pressure for the mixture. And using Dalton's law, therefore, y sub v is the partial pressure of the vapor divided by the total pressure, and y sub v sat is going to be the vapor pressure at saturation. That's the P sub g divided by the total pressure. So the total pressures cancel out, and we end up with P sub v divided by P sub g at that temperature and pressure for the total mixture. And that's a useful relationship to define the relative humidity of a moist air sample. So let's box that there. Phi is equal to P sub v divided by P sub g. Okay. The second way to define humidity, and one that's going to be very useful for a lot of our calculations, is referred to as the humidity ratio. It's also called the specific humidity. But the humidity ratio is denoted by the symbol omega, and it's defined as the mass of the water vapor divided by the mass of dry air. Not total mass of air, but of dry air. So therefore it's equal to the mass of the vapor divided by m sub a. And again, we often refer to this as the specific humidity. So we'll box that omega for our secondary definition here as the mass of vapor divided by the mass of dry air. And voila, we've got two definitions for humidity. All right, with this in mind, how do we find the properties in a mixture of water and air? Typically, these properties are going to be expressed in terms of specific quantities. Specific quantities, remember, that means per unit mass of usually the mixture itself. But in this particular case, in the case of psychrometrics, we're going to normalize the property per mass of dry air itself, not per total mass. So the m sub a, the air alone in the mixture, the mass of the air alone in the mixture, is going to be your normalizing factor. So let's go back to that enthalpy definition that we started off with, where the total extensive enthalpy is the sum of the two enthalpies of the constituents, and we're going to divide that by the mass of the dry air to illustrate the point, which means that now the enthalpy of the total mixture divided by the mass of dry air is equal to the specific enthalpy of the air within the mixture plus the humidity ratio times the enthalpy of the vapor itself. So you see that humidity ratio becomes handy. Now in practice, because of this shape of the HV diagram, now I'm just going to illustrate it here for now on the TS diagram. We'll go to the pH diagram in a moment. The enthalpy in a superheated region at a given temperature is very close to the enthalpy of the saturated saturated vapor at that same temperature. So that's how we're going to typically approximate the enthalpy of the vapor in the superheated region. And so that gives us an expression for the total enthalpy per unit mass of dry air of the total mixture. That's a bit easier to find because it's easy to find H sub g. So looking at the pH diagram to illustrate why this approximation looks good, this is kind of what a sketch of the pH diagram looks like for water. And you see that when we're in a superheated region, we're really, really close to the edge of the dome. And so therefore, that's why this is a pretty good approximation for the enthalpy of the water in the mixture itself. And again, that's kind of straightforward to pick up. Of course, with ease, things are also quite straightforward, but this is a remnant of the old days when we were using tables. Next exercise, or next part, is we're going to be talking more about dew point, another important property of moist air. So the dew point is shown here schematically. It is not the saturated pressure as we saw before. Instead, it's a temperature that corresponds to the same partial pressure as we had before. So this is what we're going to talk about next. See you in part 2.